Welcome to our second team presentation. Today we're going to review Chapter 8, Question 15 from the Norton & Company textbook. But before we dive into the problem, let's go over some essential terminology and concepts that are relevant to solve this question. First, the conservation of mass. It's a simple one. Whatever mass is present before the reaction must be present after the reaction. This law can also be applied in the context of charges. Any charges that are present on the reactant side must also be present on the product side, even if they're rearranged. This question deals with a single displacement reaction, in which an element appears to replace another element that's part of a compound. So an example from the Norton text is in the reaction where you go from hydrochloric acid and zinc to zinc chloride and hydrogen gas. In this reaction, it looks like zinc replaces hydrogen, which is why it's called a single displacement reaction. Next, let's talk about redox reactions. Redox is short for reduction and oxidation. I like to use the acronym OIL-RIG to remember which is which. OIL-RIG stands for oxidation is loss, and reduction is gain, and it refers to the number of electrons. So, in an oxidation reaction, the element that's being oxidized by means of an oxidizing agent is losing electrons, and it's becoming more positive. In a reduction reaction, the opposite happens. The element that is being reduced is gaining electrons by means of a reducing agent, and it's becoming more negative. The agent to the element being oxidized either accepts or donates electrons, depending on the type of reaction. You can track the flow of electrons by calculating the oxidation number. The oxidation number is a calculation based on what charge the ion has in the compound that it's in. Another important term to understand for solving this problem is the activity series of metals. The activity series of metals is a ranking of metals which can be looked up online in an index that helps you determine whether or not a metal ion will displace another metal ion in a single displacement reaction. This is an index that I found online, and it's determined based on stability. So, for example, if an element A were higher on this list than element B, that would mean the single displacement reaction can occur. Half-reaction spectator ions are ions that are present during the reaction but do not participate in the actual exchange. You would write the spectator ions in the balanced molecular equation, but not in the net ion equation. Basically, they're spectators to the reaction and just watch while the other ions exchange electrons. For example, in this reaction, the spectator ion, so the one that doesn't participate, is nitrate. Nitrate does not experience a transfer of electrons from the reactant side to the product side. Then next is the oxidizing agent, which is the ion doing the oxidizing. So, as we were mentioning before, since aluminum becomes more positive in the reaction for this problem, the oxidizing agent is the silver. Then conversely, the ion doing the reducing is the reducing agent. So since silver becomes more negative in our problem, as Layla will explain later, aluminum is a reducing agent. Now, connecting all of this back to the activity series of metals, in this reaction, we have aluminum displacing silver and silver nitrate. This is only possible because aluminum is higher on the activity series of metals than silver. The reverse reaction would not happen. So if you combine silver with aluminum nitrate, there would be no reaction. There are multiple ways to demonstrate the products and reactants of this displacement reaction. One is the half reaction method, which shows only the ion of focus. But it's important that you balance the appropriate number of electrons when writing this equation. For example, if electrons are being transferred out of an ion, then the electrons must be present on the right side of the equation. This method shows only the individual ion and its charges, resulting in a balanced mass and charge for the overall equation. Now that I've given you a preview of the terms, Layla will delve into the actual problem that we're solving in this presentation. Chapter 8, question 15 states, to write the balanced molecular and net ionic equations for the reaction between aluminum metal and silver nitrate. Identify the oxidation and reduction half reactions. For part 1, we will be writing out the balanced molecular equation. For part 2, the net ionic equation. For part 3, the oxidation half reaction. And for part 4, the reduction half reaction.
Okay, so in the first part of the problem, we're asked to balance the equation, but before we do any of that, we have to make sure we know what is being produced from our reactions. So the reactions are given in this equation. The first part says that we have a given of aluminum solid, and we're going to combine that with silver nitrate. So once we do that, I wrote it down. Aluminum solid plus silver nitrate yields aluminum nitrate and silver solid. So as we see, this is a single replacement reaction, and we know this because the only real difference was the metal was being swapped for the. We determine how many charges were changed from before the reaction to after. And like Hargun said, whatever is on the reactant side of the equation has to be the same elements as the other products that are on the other side of the yield. So with that in mind, we take the aluminum, which we only have one of, the silver, which we at the time only have one of before filling in the blank. Nitrogen, our given, is only one, and then we have 3 oxygens. So as we yield, after we find the products, that's when we can determine, okay, there's only one for the aluminum, again, one for the silver for now, and then on this side, we actually have 3 nitrogen and 9 oxygen. So instead of doing the big table, I kind of did a shorthand method. So what's the LCM from n equals 3 to n equals 1? Because you want to go backwards and find out how to balance it. So we plug in for 3 and solve. Then we find that there is a product of silver, and also you plug in for 3 in each. Just double check your work by making sure what's on this side. 1, 1, 3. There's 3 here. So 3, that's 9, which we balance with the 3 here. So then our final balanced equation on the bottom here is aluminum solid plus 3 silver nitrate is yielding aluminum nitrate and 3 silver solid. So then we need this because looking at the next part of the problem, we have to find the net ionic equation. So we know that finding the net ionic equation, we have to refer back to the periodic table. So we find the charge based on what column, which is also known as a group, is containing the element that we're using in the equation. So after I looked back at the periodic table, I know the first column, that's +1, second is +2. You skip the metals because they can have various different charges within them. Then the third column would be +3, and then for the fourth column, it would be either plus or minus 4. And then so on, it goes -3, -2, -1. So with that information, I was able to take those charges and fill in to find our net ionic charge for the metals that were given in the equation. What's the oxidation within this equation? Basically means what charge is being lost after the reaction takes place, which I kind of wrote a little note of here in the middle. And this is something that can also be kind of observed. So we use what we know about the ions' charges and we determine what loss was being made before the reaction and after, so that we can see that in this case aluminum is the element that loses the charge and shows oxidation. Whereas if a charge is gained, we can identify the reduction. So as we see, we're looking at the gain of electrons, and we can see that we can determine where we gained electrons based on the adding of charges. So we can see that there is more of a charge on the product side where aluminum is. So as we go back to part 4, which means think of reduction as reducing the charge of the element. So the charge is being lost as it transfers, but as the charge is being lost, that means the gain of electrons makes it a reduction reaction.
Our problem dealt with broad spectrum of knowledge from this course. First of all, writing a balanced molecular equation tested knowledge of periodic table and polyatomic ions, followed by the ability to apply law of conservation of mass to balance them. Law of conservation of mass states that the amount of products should equal amount of reactants, requiring us to have the same number of elements on left and right sides of the molecular equation. To know what kind of products we would get relied on us determining what kind of reaction we were dealing with, and in this case we worked with a single replacement reaction. This means that aluminum is going to displace silver from nitrate. For the second part of the problem, we had to determine solubility of reactants to know which of them were utilized in producing a solid product. By relying on solubility rules learned in class, we can see that solid aluminum reacted with aqueous silver nitrate, that is soluble in water, to produce aqueous aluminum nitrate and solid silver. From this information, we determined a net ionic equation that shows only the chemical species involved in the reaction, meaning production of a solid product, and this in our case was silver. During the third part of the problem, we started to delve into oxidation reduction for the reaction that we wrote and balanced. We were only tasked with finding oxidation and reaction half reactions. In order to do that, we found oxidation number for each element that we learned, determined how many electrons an element loses or gains, and traced which one loses electrons to become oxidized and which one gains to become reduced. Writing a half reaction for redox simply involved separating an element that is oxidized and its product from an element that gets reduced and its product.